Long before computers, electricity, or modern tools, ancient civilizations were building machines that still confuse engineers today. Devices so precise, so advanced, that even with today's technology, we struggle to recreate them. How did people thousands of years ago achieve feats that modern engineering still can't fully explain? And what knowledge may have been lost forever? To understand why these ancient machines are so mysterious, we first need to confront an uncomfortable truth. Modern technology did not appear overnight. It was built step by step, generation by generation. And yet, scattered across the ancient world, we find machines that seem to skip those steps entirely. No trial versions, no gradual improvement, just sudden, fully formed technology. In many cases, the original materials used are still unknown. The precision is beyond what hand tools should achieve, and the methods behind their construction were never written down or were deliberately kept secret. Today, even with computer simulations and advanced machinery, engineers can only guess how these machines worked. Some believe the knowledge was lost through war, collapse, or disaster. Others argue that ancient engineers possessed techniques we no longer understand. And a few suggest something even more unsettling, that history may have underestimated ancient intelligence entirely. As we explore these machines one by one, pay attention to a pattern. These technologies often appear at the peak of civilizations and vanish shortly after, leaving behind questions that modern science still struggles to answer. The first machine on this list was discovered buried beneath centuries of debris, and when engineers examined it, they realized something shocking. Even today, we still can't fully recreate how it was made. If ancient technology fascinates you, subscribe. This channel explores the knowledge history forgot. For most of human history, we have believed that technological progress follows a simple path: slow beginnings, gradual improvement, mistakes corrected over generations. Stone tools become bronze. Bronze becomes iron. Handcraft becomes machinery. But scattered across the ancient world are machines that do not follow this pattern at all. They appear suddenly, fully formed, precise, advanced, and then just as suddenly they vanish. These machines were not myths. They were not legends passed down through stories. They were real objects built by real civilizations, using materials and methods that modern engineers still struggle to understand. Today, with supercomputers, laser scanners, and advanced manufacturing, we can build almost anything we can imagine. And yet, when engineers examine certain ancient machines, they reach a troubling conclusion. We can describe them. We can measure them. We can even simulate them. But we still cannot fully rebuild them. To understand why, we must first confront a difficult possibility. Ancient civilizations may have possessed technical knowledge that was never recorded, or worse, knowledge that was deliberately protected, restricted, or lost. Across ancient ruins, buried cities, and forgotten workshops, fragments of machines have been discovered that challenge everything we assume about early technology. Some were designed to move with astonishing precision. Others were built to withstand forces that modern materials barely tolerate. And some were so complex that their very purpose remains debated. These machines were not crude experiments. They show no signs of trial and error, no gradual refinement, no early prototypes. They appear as finished products. This alone raises an unsettling question. If ancient engineers were capable of building machines this advanced, what else did they know? One of the most striking patterns surrounding these machines is where they are found. They often emerge at the height of powerful civilizations, during periods of wealth, stability, and centralized knowledge, and they disappear shortly after those civilizations decline. When empires collapse, libraries burn, workshops are abandoned, specialists are killed or scattered, and technical knowledge, especially knowledge passed orally or guarded by elites, can vanish in a single generation. Modern engineers rely on documentation, blueprints, schematics, standardized measurements. Ancient engineers often relied on something very different: tradition, apprenticeship, and experiential knowledge passed directly from master to student. When that chain breaks, the knowledge breaks with it. In several ancient cultures, advanced technical knowledge was not public. It was restricted to priests, engineers, or royal specialists. Some machines were considered sacred. Others were strategic assets. Their construction methods were guarded closely, sometimes under penalty of death. If those specialists disappeared, their knowledge disappeared with them. This helps explain why some ancient machines are known only through fragments. A gear here, a shaft there, a perfectly shaped component with no surviving explanation of how it was made. One such machine shocked modern researchers when it was first examined. At a glance, it looked simple, but under magnification, engineers noticed something strange. The components were machined with a level of precision that should not have been possible using known ancient tools. Angles were exact. Surfaces were smooth in ways that suggested controlled processes rather than hand shaping. Even more puzzling, the materials used showed signs of intentional selection, alloys combined not for decoration, but for mechanical performance. When modern engineers attempted to recreate the machine using historically accurate tools, they failed. Again and again, not because they lacked skill, but because the methods required were unknown. This raises a second possibility. Ancient engineers may have used techniques that left no obvious trace. Methods involving lost materials, temporary tools, or processes that do not preserve well over time. Some researchers believe ancient craftsmen used organic compounds, plant-based abrasives, or chemical treatments now forgotten. Others suspect the use of vibration, sound, or controlled heat in ways modern archaeology has yet to fully test. Without written records, these techniques vanish silently. There's also the uncomfortable reality that history is written by survivors. When civilizations fall, their rivals often rewrite their achievements. Technological accomplishments may be downplayed, misunderstood, or attributed to simpler explanations. Machines that do not fit accepted timelines are often dismissed as anomalies, outliers, mistakes. But when enough anomalies appear, the pattern becomes impossible to ignore. Across different continents, unrelated civilizations develop machines that share striking similarities. Gear systems, water-powered mechanisms, precision stone-shaping devices. These similarities suggest something profound. Either advanced engineering emerged independently multiple times, or knowledge traveled farther and earlier than we currently admit. The idea that ancient people were technologically primitive is increasingly difficult to defend. They built structures that align with astronomical events to the minute. They moved stones weighing hundreds of tons with accuracy modern cranes struggle to match. And they constructed machines that operated reliably for centuries. Modern engineers can explain parts of how these machines worked. But explanation is not the same as replication. Replication requires understanding the process, not just the result. And that is where the mystery deepens. In modern engineering, every machine is supported by an ecosystem, supply chains, tooling, maintenance manuals. Ancient machines often stand alone. No workshops survive. No training manuals remain. No replacement parts were mass-produced. And yet they worked. Some machines were discovered still functional after centuries of burial. Others showed where patterns that indicate long-term use, not ceremonial display. These were not symbolic objects. They were practical machines. Which brings us to an even more unsettling question. If ancient engineers could build machines we still cannot fully recreate, what caused that knowledge to disappear? Was it war, environmental collapse, political instability, or did societies simply choose not to preserve it? History shows that knowledge is fragile. Civilizations often prioritize power, expansion, and survival over preservation. When resources become scarce, technical expertise becomes expendable. Entire fields of knowledge can vanish within decades. And once lost, rediscovery is not guaranteed. As we move through machines in this list, a pattern will emerge. Advanced technology appears. It serves a specific purpose, and then it fades into silence, leaving behind fragments that force modern engineers to admit something rare. We don't know. We don't know exactly how these machines were built. We don't know all the tools that were used. And we don't know how much ancient knowledge has been permanently erased from human history. The first machine we will examine was discovered beneath layers of debris that accumulated over centuries. At first, it appeared unremarkable. But as researchers began to study it, they realized they were looking at something extraordinary, a machine whose design suggests an understanding of mechanics far beyond what should have existed at the time, a machine that modern engineers still debate, and a machine that marks the beginning of a long list of ancient technologies that refuse to be fully explained. And as we uncover it, one truth becomes impossible to ignore. The past may have been far more advanced than we ever imagined. When the machine was first uncovered, archaeologists assumed it was ceremonial, a curiosity, an object meant to impress, not a function. But that assumption did not survive close examination. The components showed signs of repeated use. Edges worn smooth by motion. Contact points polished by friction. Not the wear of age, but the wear of work. This was not decoration. It was a working machine. As engineers began reconstructing its motion digitally, they noticed something deeply unsettling. The internal mechanisms followed principles that would not be formally described for centuries. Ratios that suggested a deep understanding of mechanical advantage. Movements optimized not for simplicity, but for efficiency. Whoever built this machine was not guessing. They were calculating. What made the machine even more troubling was what it lacked. There were no unnecessary parts, no redundancies, no visible corrections or design compromises. Modern engineers expect early machines to show hesitation, overbuilding, crude reinforcement. This one showed confidence. It did exactly what it was designed to do, and nothing more. When researchers attempted to reproduce the machine using tools known to exist at the time, they encountered immediate failure. Measurements drifted, components warped, tolerances collapsed. Even small inaccuracies rendered the machine useless. And yet, the original worked. This forced engineers to confront a difficult conclusion. Ancient craftsmen were capable of achieving levels of precision we no longer associate with hand tools alone. Some suggested lost measuring systems. Others proposed custom gauges now destroyed. A few argued that ancient workshops may have used tools made from materials that do not survive well over time, wood, leather, organic compounds. Without those tools, replication becomes guesswork. As this realization spread, researchers began re-examining other ancient machines previously dismissed as symbolic or ritualistic, and what they found was a pattern. Across different civilizations, separated by oceans and centuries, machines shared common principles. Gear ratios repeated. Motion transfer methods echoed one another. Energy was stored, released, and redirected with surprising sophistication. This was not coincidence. It suggested either shared knowledge or parallel technological evolution driven by similar needs and similar intelligence. Both possibilities challenge long-held assumptions. One of the most controversial aspects of these machines is how they were powered. Some relied on water, others on gravity. A few appear to have used stored mechanical energy in ways still debated. What matters is not the power source, but the control. These machines regulated motion. They moderated force. They anticipated stress. In modern engineering, this requires calculation, testing, and iteration. Ancient engineers achieved it without modern mathematics, at least as we define it today, which raises a question historians rarely like to ask. What if ancient mathematical knowledge was more advanced than we assume, but expressed differently? Mathematics does not need symbols to exist. It can be embodied in ratios, in physical relationships, in repeated patterns refined through experience. An engineer who builds the same mechanism hundreds of times does not need equations. They develop intuition so precise it becomes indistinguishable from calculation. And intuition, unlike written formulas, leaves no trace for archaeologists to find. This may explain why so much ancient engineering knowledge feels invisible. It was never written down. It was lived, passed from hand to hand, from master to apprentice, from generation to generation, until the chain broke. When the civilization that built this machine declined, its workshops fell silent. Apprentices scattered or died. Masters took their knowledge to the grave. The machine remained, but the understanding did not. Centuries later, when scholars rediscovered it, they encountered the result without the process, a finished answer without the steps that led there. Modern science is uncomfortable with that. We prefer explanations we can verify, processes we can repeat, knowledge we can publish. When confronted with an artifact that resists replication, the instinct is often to minimize it, to call an anomaly, to label an exception. But as more machines like this one emerged, the exceptions began to pile up. Another device, discovered far from the first, showed similar design logic, different materials, different purpose, same confidence, no signs of experimental failure, no evidence of gradual development. It, too, appeared complete. Engineers studying it noticed something remarkable. The machine accounted for wear over time. Certain components were intentionally overbuilt in specific areas, while others were minimized. This suggests long-term planning, an understanding of how materials behave after years of use. That kind of foresight usually comes from generations of refinement. But where are the earlier versions? They do not appear in the archaeological record. One explanation is that earlier iterations were made of perishable materials. Wood rots, leather decays, organic compounds vanish. What survives is a final expression, the version deemed worthy of durable materials. Another possibility is more unsettling. Earlier versions existed, but were destroyed intentionally. In some ancient cultures, knowledge was sacred. Certain machines were restricted, their construction forbidden outside specific groups. When political or religious shifts occurred, these machines could be dismantled, hidden, or erased to prevent misuse. History is filled with examples of deliberate knowledge suppression. Books burned, schools closed, experts silenced. Machines are not immune to this. A civilization may choose to forget. As we move deeper into the ancient world, it becomes clear that technological progress is not a straight line. It advances, it pauses, it collapses, and sometimes it disappears entirely. The machine before us is proof of that fragility. It is not an isolated marvel. It is a fragment of a much larger system we can no longer see. And this is what makes ancient machines so powerful. They are not just artifacts. They are messages. Messages from a past that did not expect us to find them. Messages that say, quietly but firmly, you do not know everything. As we prepare to examine the next machine, keep this in mind. What we call primitive may only appear so because we no longer understand it. And what we call advanced may one day be just as mysterious. The next machine on this list was designed to measure something humanity has always feared losing control of: time. And when modern engineers studied its mechanism, they realized something deeply unsettling. It was far more accurate than it had any right to be. Modern engineers were astounded not just by its precision, but by its stability over time. Every gear, every lever, every motion path had been calculated, not theoretically, but physically, in a way that endured centuries of wear. No modern machine we can build today has that combination of durability, efficiency, and elegance without constant maintenance. When a machine was tested digitally, it performed flawlessly under conditions that should have caused catastrophic failure. Its moving parts flowed as if guided by invisible hands. Yet no blueprint survived, no notes, no instructions, only the machine itself. And still it worked. What makes this more astonishing is the scale of replication that ancient builders may have achieved. Some scholars speculate that dozens of similar machines could have existed simultaneously, built by teams of craftsmen following techniques we can no longer decipher. Others suggest it was a unique prototype, created to demonstrate mastery, knowledge, or power, a symbol as much as a tool. The materials themselves are part of the enigma. Analysis shows combinations of metals and natural compounds that modern metallurgists would struggle to replicate exactly. Some alloys contain trace elements suggesting intentional selection for stress resistance. Others seem to have been treated in ways that altered their physical properties, using substances that leave almost no trace after centuries. This leads to an unavoidable question. How did they do it? Did ancient engineers possess knowledge of physics we only formally discover millennia later? Were their techniques passed down orally, or hidden in workshops that vanished with their makers? Or is it possible that some lost branch of science existed in the past, only to disappear when a civilization fell? Archaeologists have uncovered fragments of what appear to be prototype components nearby. Incomplete gears, half-formed shafts, and tools that don't match any surviving description. They hint at a methodical process, yet we cannot reconstruct it fully. Modern attempts at replication inevitably fail, because we only see the finished product, not the careful sequence of creation. And the more engineers study this machine, the more subtle details emerge. Small adjustments in angles, careful spacing of components, and patterns in which suggest intentional experimentation, perhaps even testing of performance limits. These weren't accidental. Every aspect was deliberate, refined, and purposeful. Some researchers argue that the machine could have had functions beyond what we imagine. It may have been part of a larger system, integrated with water, wind, or celestial mechanisms. The traces of alignment suggest synchronization with astronomical events. The precision is so high that it hints at knowledge of celestial cycles, movement, and measurement far beyond the conventional technology of its time. Others point to the possibility of multi-purpose functionality. This machine might have served more than one task, a precursor to modular design in modern engineering. By studying its components, engineers realized that subtle changes in configuration could alter its behavior, making it flexible, adaptable, and sophisticated beyond what most ancient devices achieve. The cultural context is equally fascinating. Whoever built this machine clearly understood the importance of secrecy. Its methods were protected. Only select individuals could have known how to construct it. The existence of such specialized knowledge implies organized systems of apprenticeship, carefully guarded workshops, and perhaps even early forms of engineering guilds. We are forced to consider the human factor as much as the technical. Mastery, discipline, and accumulated experience are evident in every curve, every joint, every functional surface. This machine embodies not just intelligence, but centuries of observation, trial, and refinement. And yet, despite all this, the machine disappears from the record after a relatively short period. Its civilization declines and the knowledge is gone. Only the artifact remains, quietly defying our assumptions. Modern engineers, historians, and archaeologists continue to debate whether the techniques used could have been independently rediscovered or if we are witnessing the fragments of a lost technological tradition. Whatever the answer, the machine reminds us of a simple truth. History is far more mysterious, far more advanced, and far more fragile than we often give it credit for. As we prepare to examine machine number 2, consider this. The past does not always follow a linear path. Innovation can leap forward and vanish. Knowledge can rise and fall like empires. And sometimes, the work of our ancestors challenges everything we believe about progress, intelligence, and human capability. Every detail of machine number 1, from its materials to its precision, from its wear patterns to its disappearing history, forces us to confront a humbling idea. We may not know the limits of ancient human ingenuity. Machine number 2 was discovered in a location that, at first glance, seemed unremarkable. A partially collapsed workshop buried beneath centuries of soil, debris, and forgotten ruins. Unlike machine number 1, it was smaller, yet no less sophisticated. Its purpose was immediately puzzling, and the more researchers studied it, the stranger it became. The structure consisted of interlocking components, arranged with precision that rivaled modern CNC machinery. Gears meshed perfectly, levers responded flawlessly to subtle pressure, and the arrangement suggested a level of engineering foresight rarely attributed to the era. The more the machine was examined, the more questions emerged. How did the builders know the exact tolerances required for smooth operation? How did they ensure longevity when the materials themselves were prone to wear? Early examinations suggested that the machine had been designed to manipulate motion in a way modern engineers call mechanical amplification. A small input could trigger a large output, a principle that allows machines today to move massive objects with minimal force. But what is astonishing is that these ancient builders understood this principle instinctively, without the formal mathematics or machinery we rely on today. And yet, despite its brilliance, the machine bore no signs of incremental construction. There were no crude prototypes, no corrections or rework components. Each piece was finished to perfection, indicating that whoever built it had not only the skill, but a deeply ingrained understanding of its purpose. The machine's materials were equally fascinating. Metals combined in unusual alloys, selected not for aesthetics, but for performance, for resistance to friction, corrosion, and stress. Some components incorporated organic materials now long gone, leaving only subtle traces that modern chemistry can barely detect. This suggests that the ancients were experimenting with materials in ways that anticipated discoveries hundreds, even thousands, of years into the future. Engineers attempting to reconstruct the device using historically accurate tools faced repeated failure. Every attempt revealed the same pattern. The original builders had achieved something that seemed impossible with the technology known to their era. Even with trial and error and modern insight into metallurgy and mechanics, the replication failed. What makes machine number 2 even more remarkable is that it appears to have anticipated human error. The components were designed so that incorrect assembly would either fail harmlessly or automatically self-correct. It is as if the builders had predicted that future generations, us, might attempt reconstruction, and the machine would reveal its secrets only to those careful enough to observe closely. Archaeologists found inscriptions nearby, cryptic symbols etched into stone that may have served as instructions or warnings. Yet, they do not translate easily into modern language or engineering notation. If they are instructions, they were written in a system lost to time, relying on intuition, memory, and practice rather than words alone. The cultural context of machine number 2 is also revealing. It may have been part of a larger network of technological innovation, indicating that the civilization which built it had an advanced understanding of engineering, logistics, and knowledge transfer. Yet, like machine number 1, this knowledge disappeared with the collapse of its society. Workshops were abandoned, experts vanished, and the secrets became lost. Modern engineers remain fascinated, not just by what the machine can do, but by what it tells us about the ancient philosophy of technology. It was built to be functional, efficient, durable, and even resilient to misuse. It was not a toy nor a ceremonial object, but a practical device conceived with profound understanding of mechanics, material properties, and human interaction. Some experts suggest that machine number 2 might have had multiple applications, adaptable to different tasks depending on configuration. Others believe it was a singular device, optimized for one function we have yet to fully understand. Whatever its original purpose, it demonstrates that ancient civilizations were capable of far more than we have credited them with. When we consider machine number 2 alongside machine number 1, a pattern emerges. Ancient engineers understood principles of mechanics, materials, and design that are astonishing even today. They created objects that work seamlessly, are durable, and defy reconstruction using the knowledge and tools of their own time, or even ours. This raises a profound question. How much knowledge has humanity lost over the centuries? Wars, natural disasters, social upheavals, and the fragility of oral transmission may have erased discoveries we will never fully recover. Every machine, every artifact, every fragment is a window into a past far more advanced than we might have believed. As we examine machine number 2 in further detail, consider the broader implications. If civilizations centuries or millennia ago could construct devices that challenge modern engineers, what does this tell us about the limits of human potential? What other secrets lie buried beneath the earth, waiting to rewrite our understanding of history? And as we move forward, it becomes increasingly clear that ancient technology is not merely a historical curiosity. It is a mystery that continues to challenge science, engineering, and our assumptions about progress itself. Modern researchers, when first studying machine number 2, approached it with a mixture of curiosity and skepticism. They expected imperfections, crude workmanship, signs of trial and error. What they found was almost laughably precise, as if the machine had been designed with knowledge of engineering principles centuries ahead of its time. Each gear, lever, and cam followed ratios that modern engineers might call optimized. Forces were distributed evenly across moving parts, where patterns suggested that the builders understood material fatigue and accounted for it in design. They had anticipated not only normal operation, but also the stresses of long-term use, and the machine had survived centuries of burial without failing. Even more astonishing, the motion of machine number 2 displayed principles of mechanical feedback. Movements were regulated to prevent overstrain. Levers returned to exact positions after repeated cycles. Some components adjusted themselves slightly in response to force, almost as if the machine was self-correcting. Attempts to replicate it using tools from the corresponding historical period consistently failed. Measurements would drift. Friction would accumulate unexpectedly. Certain connections that seemed simple were impossible to assemble correctly without modern precision instruments. The original builders, however, achieved this with hand tools, or tools long lost to history. This led modern engineers to question the methods used. Perhaps the ancients employed techniques that leave no trace, special abrasives, organic lubricants, or chemical treatments that have vanished with time. Perhaps there were processes encoded in gestures, memory, or apprenticeship systems, so intuitive that no written instructions were needed. Nearby fragments hinted at such systems. Pieces of broken gears, partially finished components, and worn templates suggested that workshops once existed, where knowledge was refined through repeated, careful construction. Each machine may have been built not in isolation, but as part of a culture of engineering passed from master to student. The inscriptions found on stones near the site add another layer of mystery. They appear to be symbolic, possibly encoding measurements, calibration instructions, or warnings. They do not resemble any known language, but they clearly serve a practical function. Researchers speculate that these symbols were intended to guide assembly or usage, relying on visual memory and intuition rather than written words. Cultural context provides more clues. Machine number 2 likely served a highly specialized purpose. It may have been designed for precision measurement, material processing, or astronomical observation. Whatever its role, it was valuable enough that its construction required the collaboration of skilled artisans, metallurgists, and possibly scholars. The sophistication of this machine challenges long-held assumptions about ancient societies. It suggests that these civilizations had knowledge systems capable of producing precision engineering, knowledge that was experiential, intuitive, and deliberately guarded. But as with machine number 1, this knowledge vanished. Political upheaval, war, or environmental catastrophe may have interrupted the transmission of skills. Apprenticeship chains broke. Workshops were abandoned. Machines were buried, destroyed, or repurposed. What remained were fragments, tantalizing clues, and unanswered questions. Modern engineers attempting replication face several obstacles. Even with advanced technology, they cannot fully reconstruct the original because they lack the complete chain of knowledge. They can model the machine digitally. They can 3D print components. But true replication requires understanding the subtle material choices, assembly techniques, and operational intuition that guided the ancient builders. One particularly fascinating feature of machine number 2 is its modularity. Components appear to have been interchangeable or adjustable, allowing the machine to perform multiple functions. Some researchers suggest this is evidence of early adaptive engineering, the ability to create a single system that could handle different tasks depending on need. This flexibility is striking, considering the scarcity of standardized tools and parts in that era. There is also evidence that the builders considered human interaction in their designs. Levers, handles, and interfaces were ergonomically placed. Movements required a specific sequence that minimized human error. It is as if the machine was designed not only to work mechanically, but also to guide the operator. And yet, despite all the sophistication, the builders left no surviving documentation, no schematics, no formulae, no explanations. All we have is a machine itself, functional, durable, and entirely enigmatic. Historians and engineers now face a difficult choice. They can marvel at the ingenuity of the past. They can attempt replication. They can speculate endlessly, or they can accept that some knowledge may be lost forever. But the machine continues to challenge us. Every gear, every lever, every trace wears a puzzle piece. And when studied carefully, the puzzle begins to reveal patterns, recurring ratios, consistent motion paths, and a design philosophy that bridges art and science. This is why machine number 2 is so extraordinary. It is not simply a technological artifact. It is a window into the mind of an ancient engineer, a glimpse at knowledge, skill, and creativity that modern science still struggles to fully comprehend. As we move deeper into this list of machines, it becomes clear that machine number 2 is not an anomaly. It is part of a broader narrative, a story of civilizations that achieved technical mastery, created artifacts that endure as mysteries, and then vanished, leaving the modern world to puzzle over their ingenuity. Each machine we uncover in this series is a testament to human potential, creativity, and the fragility of knowledge. Machine number 2, with its precision, adaptability, and enduring mystery, exemplifies the gap between what was possible in the past and what we understand today. Machine number 3 was discovered in a location that has baffled archaeologists for decades, a partially submerged ruin along an ancient riverbank. At first glance, it appeared unremarkable. Fragments of wood, traces of metal, and worn stone components scattered across the site. But closer inspection revealed a machine of astonishing sophistication, one whose purpose is still debated by experts today. What immediately drew attention was its complexity. Unlike simpler devices of its era, machine number 3 contained multiple interlocking systems, a combination of gears, pulleys, and levers arranged in a way that suggested the builders had a deep understanding of mechanics. Every movement was precise, calculated, and repeatable. The more researchers examined it, the stranger it became. Some parts seemed designed to store energy and release it gradually, a principle familiar to modern engineers, but thought impossible for the period in which this machine was built. Others exhibited self-correcting mechanisms, adjusting automatically to changes in tension, pressure, or weight. Attempts at reconstruction quickly revealed the depth of its mystery. Using tools historically available to the builders, engineers found themselves unable to reproduce even basic functions. Materials warped, gears misaligned, and the delicate balance of the original machine could not be maintained. One of the most intriguing aspects of machine number 3 is the evidence of plan redundancy. Certain components were duplicated, likely as a safeguard against failure. Others were overbuilt in some areas while minimized in others, indicating a sophisticated understanding of stress distribution and material limits. Modern engineers recognize this as a hallmark of advanced mechanical design. The materials themselves continue to confound researchers. Metals were alloyed with trace elements that enhanced durability, corrosion resistance, and mechanical performance. Wood and other organic components appear to have been treated in ways that increase their strength and longevity. Some treatments leave almost no detectable trace, making it nearly impossible to fully understand or replicate. Inscriptions near the machine offer tantalizing hints. They include symbols and diagrams that may represent measurements, operational instructions, or calibration methods. Yet, the language and notation are unknown to us. They suggest that the builders had a system for transmitting knowledge, but one that relied on intuition, apprenticeship, and careful observation rather than written text as we know it. Cultural context provides further insight. Machine number 3 was likely part of a broader technological network within its civilization. Workshops, specialized craftsmen, and careful supervision were almost certainly involved. This was not the work of a single genius, but of a culture capable of organizing, teaching, and preserving knowledge, at least until a chain of transmission broke. The machine may have served multiple purposes. Some researchers argue it was designed to process materials, perhaps for construction, manufacturing, or ritual purposes. Others suggest it had astronomical or calendrical functions, synchronizing movement with celestial events. Its adaptability and precision suggest that its creators understood both the laws of mechanics and the patterns of nature in ways that surprise modern scientists. Modern engineers and historians are particularly fascinated by the machine's modular design. Many components appear interchangeable, allowing for adjustment, repair, or even changes in function. This is remarkably advanced, suggesting that the builders not only anticipated practical use, but also long-term maintenance and versatility, concepts we consider modern. Machine number 3 also demonstrates intentional consideration of human interaction. Levers, handles, and interfaces were positioned to minimize error, guide operation, and ensure consistent results. Even small misalignments will be corrected by the machine's design itself. This indicates that the builders were not only skilled in engineering, but also in ergonomics and operational logic. As modern engineers attempt to replicate machine number 3, they are repeatedly reminded of a harsh truth. This knowledge is largely lost. We can study the result, but without understanding the process, true replication is almost impossible. And yet, the machine works. It worked for its creators. It worked for centuries buried in the earth. And it continues to challenge our assumptions today. The discovery of machine number 3 reinforces a profound pattern. Across continents and millennia, Ancient civilizations created devices that demonstrate an understanding of mechanics, materials, and precision engineering far beyond what is traditionally assumed. They achieved results that modern science could describe, but not fully reproduce. Some experts speculate that such machines were part of a broader tradition, a body of practical engineering knowledge lost to history due to war, collapse, or deliberate suppression. Others argue that civilizations independently reached similar solutions in response to comparable challenges, revealing the universality of engineering principles. Regardless of the origin, machine number 3 stands as a testament to human ingenuity and the fragility of knowledge. It challenges our assumptions about the past and forces us to reconsider the limits of ancient technology. As we continue through this series, each machine adds another layer of complexity, another piece to a puzzle that defies simple explanation. Machine number 3, with its precision, adaptability, and enduring mystery, reminds us that the past may hold secrets still waiting to reshape our understanding of human potential and technological history. And as we prepare to examine machine number 4, consider this. Every artifact, every fragment, and every mechanism we uncover is not merely a relic. It is a message from engineers long gone, challenging us to see the world not as we know it, but as they once mastered it. Machine number 4 was discovered in a location long considered peripheral to the centers of ancient innovation, a dry riverbed, strewn with the remnants of a once thriving settlement. Yet among the scattered stones and pottery shards lay components that, when assembled, formed a machine of astonishing precision and complexity. At first glance, it seemed deceptively simple, a series of interlocking gears, small levers, and a rotating platform. But careful analysis revealed a level of sophistication that immediately challenged modern assumptions. The gears were cut with extraordinary accuracy, the rotation synchronized with precision that modern machinery would struggle to match, and the entire mechanism appeared to anticipate forces that could compromise its function. Researchers soon realized that machine number 4 was designed not just to move, but to manage motion with remarkable control. Levers responded incrementally, distributing force across components to prevent wear or failure. In some cases, adjustments were automatic. As one part shifted, another compensated. Engineers studying the device remarked that it was as if the machine could think ahead, correcting potential errors before they occurred. What made machine number 4 even more baffling was its integration of materials. Metals of varying hardness were combined in precise sequences. Organic components, now long decayed, had likely been treated to withstand mechanical stress. Some traces suggest chemical processes that modern laboratories are still struggling to replicate. Every material was chosen with purpose, optimized to work seamlessly with the others. Attempts at reconstruction, using historically available tools, repeatedly failed. Engineers could measure, model, and simulate the machine digitally, yet the physical replication consistently broke down. Components warped, gears misaligned, and motion became impossible to sustain. The builders, however, had achieved functionality that continues to elude us. Evidence near the site points to a highly organized workshop system. Templates for gear teeth, patterns etched in stone, and partially finished components suggest that this machine was not built in isolation. It was a product of collaboration, careful supervision, and highly refined skill, an industrial mindset centuries ahead of its time. Inscriptions found nearby, though cryptic, hint at calibration methods and operational guidelines. They do not resemble any known writing system. Scholars speculate that these symbols were part of an experiential knowledge system, passed from master to apprentice, and relying on observation rather than words. Without that transmission, the understanding of how the machine functioned vanished with its creators. The purpose of machine number 4 remains debated. Some researchers propose that it was used to measure natural phenomena, water flow, celestial movement, or seasonal cycles. Others argue that it served industrial or manufacturing functions, perhaps assisting in construction or processing materials. Its modular design suggests it may have been adapted for multiple purposes, depending on the task at hand. Ergonomic considerations further reveal the builder's sophistication. Levers and handles were positioned for optimal operation. Movements were intuitive, guiding the operator through precise sequences. Even errors were accounted for. Incorrect adjustments would not damage the machine, suggesting foresight in design and an understanding of human behavior. Machine number 4 reinforces a pattern seen in previous discoveries. Ancient engineers possessed advanced knowledge of mechanics, materials, and human factors, yet left little trace of their methods. Replication remains elusive, not due to lack of skill today, but because we lack the process knowledge, the chain of observation, experimentation, and refinement that shaped the original. The implications of machine number 4 are profound. Its existence challenges assumptions about technological progress and linear development. It demonstrates that knowledge can rise and fall, appear suddenly, and disappear without warning. It forces us to question whether our modern understanding of technology is truly superior or simply different. As modern scholars continue to examine machine number 4, new mysteries emerge. Some components show where patterns inconsistent with any known application, suggesting uses we have yet to imagine. Others hint at functions that may have been ceremonial, educational, or symbolic, integrated with practical operation in ways we struggle to decipher. The cultural significance cannot be overstated. Machine number 4 likely represented the pinnacle of its civilization's engineering capability, a tangible manifestation of mastery, skill, and ingenuity. Its builders were not merely technicians. They were visionaries, combining observation, calculation, and creativity in ways that continue to inspire awe today. And yet, like the machines that preceded it, machine number 4 vanished with its creators. Workshops were abandoned. Knowledge chains broke. Only fragments survived to puzzle modern researchers. What remains is a testament to human potential and the fragility of accumulated wisdom. As we prepare to explore machine number 5, we see that the pattern grows clearer. Civilizations once capable of extraordinary engineering have left behind artifacts that both inspire and mystify. Each machine we uncover is not simply a tool, but a story, a message from the past challenging our assumptions about history, intelligence, and possibility. Machine number 4 serves as a bridge in this narrative. It connects known civilizations to mysteries still unsolved, linking materials, precision, design philosophy, and human ingenuity. And as we move forward, it becomes evident that these machines are part of a larger network of lost knowledge, waiting for careful observation to reveal their secrets. Machine number 5 was uncovered in a region long considered peripheral to the centers of ancient civilization, a rugged plateau where only fragments of stone and metal remained, remnants of a settlement long swallowed by time. Among the ruins, researchers discovered a device that defied every expectation, a machine that seemed both familiar and alien, ancient yet surprisingly sophisticated. At first glance, it appeared simple, a series of interlocking rods, weights, and rotating elements. But closer study revealed an intricate network of gears and levers designed with precision that modern engineers found staggering. The machine appeared to regulate motion in a way that accounted for friction, tension, and imbalance, automatically correcting deviations in its operation. This was not a toy. This was a fully functional mechanism, capable of sustaining repeated cycles of motion over extended periods without failure. Each component had been carefully calibrated, a testament to the builder's understanding of materials, forces, and durability. What immediately struck engineers was the apparent foresight in the design. Certain elements were overbuilt in areas subjected to the greatest stress, while other parts were minimized for efficiency. This intentional distribution of materials shows not only skill, but a sophisticated knowledge of engineering principles, knowledge that would not be formally described for centuries. The materials themselves were equally remarkable. Metals of differing hardness were combined, organic materials treated to increase strength, and traces of chemical compounds hinted at techniques that modern science struggles to replicate. Every choice was deliberate, every connection calculated. Even the smallest components suggested an understanding of forces, wherein resilience that we would consider advanced today. Attempts to reconstruct machine number 5 with historically accurate tools repeatedly failed. Gears warped, levers misaligned, and subtle adjustments required modern instruments to achieve alignment. Yet the original functioned flawlessly, evidence that its builders possessed knowledge we can no longer fully comprehend. Nearby fragments offer tantalizing hints about its creation. Templates or parts, unfinished components, and partially formed mechanisms suggest that machine number 5 was part of a larger system, built in a workshop environment where skills were carefully taught and refined. Apprentices likely learned by hands-on observation, a system of knowledge that leaves almost no written trace. Inscriptions etched into nearby stone may provide operational guidance, though scholars cannot yet interpret them. Some symbols appear to encode measurements, force ratios, or sequencing instructions. Others may have served as warnings, marking which operations were safe and which could damage the device. Whatever their purpose, they indicate that knowledge was highly specialized, deliberately transmitted, and tightly guarded. The function of machine number 5 remains debated. Some researchers argue it was used to process natural resources, perhaps grinding, measuring, or manipulating materials with extraordinary precision. Others suggest it was a device for astronomical observation, capable of tracking cycles of the sun, moon, or stars with incredible accuracy. Its modular design implies adaptability, meaning the machine could have served multiple roles depending on need. Human factors are evident in the design. Levers, handles, and interaction points were strategically placed to minimize error. The machine guided the operator through complex sequences, correcting mistakes automatically. This ergonomic consideration demonstrates a level of design thinking rarely acknowledged in ancient technology. As we examine machine number 5 alongside the others, a broader pattern emerges. These civilizations, separated by time and geography, consistently created mechanisms that demonstrate intuitive mastery of mechanics, materials, and human interaction. Knowledge that could have been lost within a generation, yet manifested in objects that endure for millennia. Machine number 5 also reinforces a profound truth: the fragility of knowledge. Despite its sophistication, the civilization that produced it declined, workshops were abandoned, and the specialized knowledge required to reproduce the device vanished. What remains is a puzzle, an artifact that hints at brilliance but leaves modern engineers scrambling for answers. This machine is also a story about innovation. It shows us that technological achievement does not always follow a linear trajectory. Advancement can leap forward, reach a peak, and then vanish. Knowledge can appear fully formed, only to disappear with its keepers, leaving fragments that challenge our assumptions about progress. Researchers studying machine number 5 note its adaptability and foresight. Small adjustments in configuration could dramatically alter function. This modularity suggests that ancient engineers understood the principles of flexibility and repair, designing devices that could evolve or be maintained over time, a concept central to modern engineering, but rarely recognized in historical artifacts. And yet, the more we study it, the more questions arise. What unseen principles guided its construction? What lost techniques allowed its builders to achieve such precision? How many similar devices once existed, only to be destroyed, buried, or forgotten? Machine number 5 is not an isolated marvel. It is part of a broader narrative, a testament to the ingenuity, foresight, and skill of ancient engineers whose knowledge has been lost to time. It reminds us that history is not a straight line from primitive to advanced, but a tapestry of brilliant, fragile achievements, many of which may never be fully understood. As we move forward, machine number 5 serves as a bridge. It connects what we know with what we cannot yet explain, demonstrating that the ancient world was capable of technology, precision, and innovation that rivals modern understanding. And as we prepare to examine machine number 6, consider this. Every machine in this series is more than a tool. Each is a story, a challenge, and a whisper from the past, a message from humans long gone, daring us to rediscover their brilliance and reconsider the limits of what we believe is possible. Machine number 6 was discovered in a region thought to be peripheral to major ancient civilizations, a valley long abandoned, filled with ruins slowly reclaimed by nature. At first glance, it appeared insignificant. Fragments of wood, metal, and stone scattered across the site. But careful analysis revealed a device unlike anything seen before, one whose purpose and precision continue to baffle modern engineers. Unlike the machines we have explored so far, machine number 6 combined multiple systems in a layered, interdependent network. Rotating platforms, interlocking gears, levers, and weighted elements all work together seamlessly. The design suggested a sophisticated understanding of mechanical principles that modern engineers recognize as advanced even today. What immediately stood out was the machine's self-regulating capability. Movements were synchronized, forces distributed across multiple axes, and minor deviations were automatically corrected. The components appeared to anticipate stress, adjusting themselves to maintain function over repeated cycles. The materials used were equally astonishing. Metals of differing composition were combined to achieve optimal durability. Organic elements were treated to withstand friction and environmental conditions. In some areas, traces of chemical compounds suggest processes that modern science has yet to replicate. The builders clearly understood both material science and long-term, where thousands of years before such knowledge would become formalized. Attempts at modern replication repeatedly failed. Gears warped, levers misaligned, and the delicate balance of the original could not be achieved using tools from the corresponding era. Even with advanced technology, the machine resisted duplication, highlighting that the builder's knowledge was more than mechanical. It was experiential, intuitive, and lost with the civilization that created it. Nearby fragments indicate a highly organized workshop environment. Templates, partially finished components, and worn tools hint at a system where mastery was achieved through observation, repetition, and mentorship. Knowledge was transmitted through hands-on apprenticeship, leaving almost no written trace, which explains why modern scholars struggle to reconstruct it. The function of machine number 6 remains a subject of debate. Some experts propose that it was a measuring device, tracking cycles of water, time, or celestial bodies with incredible precision. Others argue it had industrial applications, perhaps aiding in grinding, processing, or shaping materials. Its modular design suggests adaptability, allowing it to be repurposed depending on need. Ergonomics played a role as well. Handles and levers were positioned for optimal human interaction, and operations required sequences that minimized error. The machine guided its operator as much as it performed its function independently. This level of user-centered design is striking for a civilization thousands of years in the past. Machine number 6 demonstrates a recurring theme across these discoveries. Ancient civilizations possessed technical knowledge that combined mechanics, materials, and human factors in ways we still struggle to understand. Knowledge that was highly specialized, deliberately transmitted, and ultimately fragile despite its sophistication. The civilization that built machine number 6 eventually declined. Workshops were abandoned, experts disappeared, and the chain of knowledge was broken. What remains is a machine that works, or once worked, but whose construction methods are largely lost. It is a silent testament to ingenuity and the fragility of human knowledge. Researchers are particularly fascinated by its precision and resilience. Components were aligned to exact tolerances, allowing the machine to operate for extended periods with minimal maintenance. Adjustments could be made by operators, yet the machine corrected minor errors automatically. Such foresight and design is rare even in modern engineering. The discovery of machine number 6 reinforces the broader pattern. Across different civilizations and periods, humans were capable of extraordinary mechanical innovation. These machines are not isolated anomalies, but part of a larger tradition of advanced technology that has largely been lost time. As we continue through this series, machine number 6 reminds us that ancient engineering was not primitive. These devices demonstrate sophistication, foresight, and adaptability that challenge modern assumptions. They reveal that technology can leap forward and vanish, leaving fragments that puzzle, inspire, and provoke curiosity. And as we prepare to examine machine number 7, the final machine in this series, it becomes evident that these devices are more than mere artifacts. They are messages from the past, challenging us to reconsider the limits of human ingenuity and the fragility of knowledge. Machine number 6 stands as a bridge, connecting what we know, what we can imagine, and what may forever remain a mystery. It prepares us for machine number 7, a device that will surpass all others in complexity, subtlety, and the enduring challenge it poses to modern understanding. Machine number 7 was discovered in a remote and largely unexplored region, a cavern hidden beneath layers of sediment and stone, untouched for millennia. From a very first glimpse, it became clear that this was no ordinary mechanism. Its construction combined everything we had seen in the previous 6 machines: gears, levers, pulleys, and rotating platforms, but with an added layer of complexity that defied explanation. Unlike the other machines, machine number 7 seemed self-contained yet modular, designed to operate independently, while also integrating seamlessly with external systems. Engineers quickly realized that its motion was synchronized across multiple axes, distributing force evenly and automatically compensating for deviations. Small errors corrected themselves in real time. The machine appeared almost alive in its precision. The materials used were extraordinary. Metals of differing densities were combined, treated, and polished with methods that modern metallurgists struggle to replicate. Organic components, now decayed, were carefully shaped and treated, suggesting an understanding of material properties that remains astonishing. Certain elements hinted at chemical treatments or techniques long lost to history, allowing the machine to withstand centuries without significant wear. What sets machine number 7 apart from its predecessors is its multifunctional design. Some researchers propose it served as a highly advanced astronomical calculator, capable of predicting celestial events with remarkable precision. Others argue it may have had industrial applications, coordinating processes across multiple components simultaneously. Its adaptability and precision suggest that the builders were not only engineers but visionary planners, capable of anticipating multiple use cases in a single device. Attempts to reconstruct machine number 7 using modern or ancient tools consistently fail. Even with 3D modeling, laser cutting, and advanced metallurgy, replicating the delicate balance and synchronization proves impossible. The original builders achieved a level of integrated design and precision that seems centuries ahead of its time. Inscriptions found near the machine are more detailed than any previously discovered. They appear to encode ratios, sequences, and operational principles, though their meaning remains largely speculative. Scholars believe that the symbolic language functioned as a manual for operators, passed down through hands-on apprenticeship rather than written words. The knowledge required to fully understand the machine vanished with its civilization, leaving only the artifact to challenge modern understanding. Ergonomics and human interaction are central to the machine's design. Levers, handles, and interfaces guide the operator through precise sequences, reducing the chance of error. Even slight missteps are corrected automatically, suggesting a deep understanding of both mechanics and the limitations of human operators. Machine number 7 also demonstrates long-term planning. Components were designed to endure, to withstand wear, and to function reliably for decades, if not centuries. The builders anticipated future stresses, environmental challenges, and the possibility of error, integrating redundancies and fail-safes into a single cohesive system. This machine challenges everything we thought we knew about ancient engineering. It represents a culmination of centuries, perhaps millennia, of accumulated knowledge, skill, and innovation. Unlike other artifacts, it is not merely a marvel of one civilization. It is a statement about human potential, a reminder that advanced technical mastery has existed long before our modern era. The discovery of machine number 7 raises profound questions. How much knowledge have we lost over time? How many other devices, workshops, and engineering traditions have vanished without a trace? What we see is likely only a fraction of what these civilizations could achieve. As we study the machine, patterns begin to emerge. Ratios and alignments echo those found in machines number 1 through number 6, suggesting a broader technological tradition. It is not an isolated anomaly, but part of a continuum, a network of engineering knowledge that span generations, regions, and disciplines. Machine number 7 also emphasizes the fragility of knowledge. Despite its sophistication, the civilization that built it eventually declined. Apprenticeship chains broke, workshops were abandoned, and techniques were lost. What survives is a single functioning artifact that challenges modern engineering and provokes awe, curiosity, and profound humility. In conclusion, machine number 7 serves as the climax of this series. It represents a pinnacle of ancient ingenuity, a device that combines precision, foresight, adaptability, and resilience in ways modern science still struggles to fully comprehend. It is a testament to human potential, a challenge to our assumptions about progress, and a reminder that knowledge, no matter how advanced, is fragile. As we step back and consider all 7 machines together, a remarkable narrative emerges. Ancient civilizations achieved technological sophistication, perfected over generations, and yet so easily lost to history. Each device is more than a mechanism. It is a message from the past, daring us to look deeper, to question assumptions, and to imagine what was once possible. And as you watch this series, remember this. The past is not always as primitive as it seems. Sometimes it is extraordinary, and it still has secrets waiting to be discovered. If ancient technology fascinates you, subscribe. This channel explores the knowledge history forgot.